Hi everyone, this is Mrs. Stern, and we are going to talk today about batteries because of the way that batteries involve everything you've been learning about redox chemistry and single replacement reactions. So batteries are kind of this interesting intersection between things you may have learned in physics and things you've learned in chemistry. So just to review, electricity is the flow of electrons, and electrons are very involved in redox reactions. So we measure electrical potential using volts, which is why you may have seen batteries labeled like a 9-volt battery or something like that. And you learned from the TED Ed video that that unit was named for Alessandro Volta, who was really important in inventing batteries. Batteries involve redox reactions where there are chemical reactions transferring electrons. And that's basically all a battery is. It uses redox reactions to produce electricity. So in the TED Ed video, you learned a little bit about how batteries work, and we're just going to go into that in a little bit more detail. So essentially within a battery, there's an oxidation reaction taking place and a reduction reaction taking place, and they're separated into two separate containers where there are neutral metals placed into an electrolyte solution. So this diagram is kind of a very simplified diagram of how a battery works. If we were actually in class, we could really build a battery like this using beakers and pieces of metal. But in those electrolyte solutions, you're going to have ions, because that's the definition of an electrolyte. And there's going to be a redox reaction that takes place that will cause electrons to spontaneously flow from the oxidation reaction to the reduction reaction. So let's break this down so you can see how this works. So let's imagine you have two beakers or little containers. And in both of those, there's an aqueous solution with ions in it. So we have zinc ions over here. Maybe we have like a zinc sulfate solution or something like that in this container. And let's say we have a copper sulfate solution in this container. And then we have a piece of zinc metal and a piece of copper metal. These were the two metals that were shown in the TED Ed video you just watched. So this would be the balanced single replacement reaction. So we have zinc, which is here, that's going to react with copper sulfate. And so really the single replacement reaction is happening with this zinc and this copper ion, because we're imagining there's like copper sulfate in this container. And so if we think about which element is being oxidized and which element's being reduced, you could look on the back of your periodic table and find zinc and copper. You would see zinc is much higher on the activity series, so zinc is able to replace copper. And so the oxidation reaction will happen over here because zinc is going to go from having a charge of 0 to having a charge of +2. That means that zinc has lost 2 electrons. Well, this copper over here in this container would really like to gain some electrons. And so that's really how the battery works, is that these electrons are going to be given up by the zinc and they're going to be accepted over here by this copper. So let's kind of animate how that happens. So imagine here we have a neutral zinc atom hanging out on this bar of zinc here. And here we have a +2 copper ion in the solution. When this zinc gets oxidized, that zinc atom is no longer going to be part of this solid metal. It's going to fall off into the solution and dissolve in the water. And so now we're just like accumulating zinc ions in this solution. These electrons are now free to flow, and they're going to flow spontaneously. There's no energy being added. It's just that this copper would really like to accept them. So there they go. They flow through the wire. They can be used to power anything that works on electrical power. And then when the electrons get over here, this copper snatches those electrons. And once that copper with its +2 charge accepts those 2 electrons, it neutralizes and becomes a solid copper atom. So that's essentially an animation of what's happening here. Zinc gave up its 2 electrons, copper accepted them, and then this is our end product. We produced a copper atom right there. Remember that got produced? And we produced this zinc +2 atom, which is over here. So if you were actually to do this, this is what it would kind of end up looking like, that the zinc over time would get kind of worn down because you're constantly oxidizing these zinc atoms, and then they're dissolving in the water. So the solid neutral zinc on this bar is going away. And in the meantime, this piece of copper is going to start getting like more crystals building up on the outside of it, because copper from this solution is accumulating on the copper bar as it gets neutralized by the electrons. So we do have some general terms we use to talk about the parts of a battery. The metal that's oxidized, in other words, the metal that's losing its electrons, is called the anode. So here we have a zinc anode. The copper is a metal that is being reduced, so we would call the copper the cathode. So all batteries have an anode and a cathode. They could be made out of different metals depending on which chemical reaction is being used in that battery. So not all batteries have zinc and copper. Like you might have heard of batteries having lithium. There's other metals that are used commonly in batteries. And then because of the fact that electrons are constantly flowing in this reaction from the anode to the cathode, you get electrons building up over here at the cathode end. And so batteries will also contain something called a salt bridge, which is a gel containing some kind of electrolyte that will help those electrons to kind of move back through and rebalance the charge. It's also worth noting that in many batteries, the electrolyte solution is either acidic or basic. Another word for basic is alkaline. So even though here I'm only showing the zinc ions and the copper ions, you do have some anions in this solution that I just didn't show because they're not participating in the reaction. And you may have hydrogen ions or hydroxide ions, which would either make the battery acidic or make the battery alkaline. So when you've heard of battery acid before, or if you've heard of alkaline batteries, that's what that is referring to. Lastly, I just want to talk about rechargeable batteries, because if you think about that picture that I showed a couple slides ago where that zinc is getting worn down, batteries only have a certain amount of life to them because the anode is getting like physically worn down as the metal oxidizes. And so the way that a rechargeable battery works is that you apply electricity to force the redox reaction in the non-spontaneous direction. You are essentially like reversing that chemical reaction by applying some energy to it. And so then you're using electrical energy, coming through your power outlet to convert it back into chemical energy inside your battery. That's how rechargeable batteries work. And, different batteries are more efficient at recharging than others. And so they do still have a lifespan to them, but that's kind of how that works. So hopefully this is a good way for you to understand a little bit more about how oxidation reduction reactions and single replacement reactions play out in the real world in the technology of batteries.